Hello again everyone, welcome back to another video on axiomatic thermodynamics, and today we are going to talk about phase changes and phase diagrams. In one of the earlier videos we did see that phase diagrams can be written as either P versus V or P versus T, but in the two examples that we will be seeing right now in today's videos, is gonna be mostly on T, so I'm gonna go ahead and remove the V again. So again, what are actually phase transitions? We know from the common example of the most common chemical that we use in our daily lives, which is water, that water exists in either ice, which is a solid state, water in the fluid state, or vapor, which is the gaseous state. And we do realize when we increase the temperature on the y-axis, as the energy also increases in the x-axis. We have all learned around some time in our schools that at some point the temperature ceases to increase, but the energy increases nevertheless. And this extra energy that a system needs for the phase transition is called the latent heat. And that is exactly seen here when the temperature increases until, let's say, 0 degrees, and then it stays constant for some time, even though the energy is increasing on the x-axis. And this is the extra energy that it needs to basically break the bonds in between the water molecules in its solid state, so that it can actually transition itself into the water, fluid water state. And that can be seen very nicely in this phase diagram, where we have the P on the y-axis and the T on the x-axis. And we have these very nice lines, the lower one being the sublimation line, the upper one being the vaporization or evaporation line, and this one being the melting line. And what we basically see here is that on these lines are where the phase transitions happen. So as we could probably already think of from now, that this area basically represents solid water, so ice. This one is for liquid water, which is the water that we drink, we know. And this one would be then for vapor, so gas. So these are the three regions, this one being for solid, this one for liquid, and this one for gas, which we can clearly make a sense of from the phase diagrams. And these are the lines where as the temperature increases or as the pressure changes, gaseous water can also become solid, or solid water can also become gaseous. This is not only very specific to water, but this can happen to basically any chemical. We will also be seeing another example of nitrogen later on. But this is basically one of the most important uses of a phase diagram. And it is not only these lines which are important, but it is also this point and this point, which are also very important. And this little point that we see here, this is called a triple point. And as we can kind of guess from how to read the phase diagrams, we can kind of guess that at this point, water in general should have all the three phases existing parallelly. Which sounds crazy at first, but is actually much real. Like, it can be actually shown in many such examples of experiments, that there are chemicals in which you can find all the three states existing at once at the same time, given a certain temperature and certain pressure. And this is called then a triple point. And for water, it is actually around 273,16 Kelvin, or around 0.01 degrees Celsius. I wrote in both the units. I do not really know which units you would be using. and also around the temperature of around the pressure of 0.006 bar, which is basically 6 millibar. So at this exact point, one can find water in ice, liquid water and vapor form together. And what is this point around here? This is also called the critical point. For water, it comes at around, I can first write it as critical point. And it first comes, like for water, it comes out at 647 Kelvin and 218 bar. This is a very interesting point in the phase diagram where you can actually not make any difference between a liquid and gas phase boundaries. So basically, if you have a circular kind of a flask where let's say until this point you could see where the water was and where the vapor was. However, at the critical point, when you reach the critical point, then this boundary basically vanishes and you would see something like this, whereby you would probably have just a thick fog of some kind, and you would not be able to actually make out what the boundary of the phase was. And this is certainly a very interesting point in the phase diagram, one that is not really studied that often in educational institutes, but yeah, it's really a crazy point. Right, and then we can also move on to the next example, which would be, sorry, I still have the highlighter on, which would be of nitrogen. Nitrogen also has a similar kind of a graph, whereby we also have a triple point here and a critical point here, and rest of the stuff are also the same. I should probably mark here that this is for water, and now this is for nitrogen. In nitrogen's case, the triple point would be at around 63 Kelvin, and the pressure would be at around 0.13 bar. So the y-axis again denotes P, which is pressure, and the x-axis T, which is temperature. And the critical point appears at around 126 Kelvin and 35 bar. And it is again the same thing. This part here would signify solid nitrogen, this part here liquid, and this part here gaseous. And this is again the sublimation curve, this is the melting curve, and this is the evaporation or vaporizing curve. Right, so that is most of the important stuff that I wanted to say about phase diagrams. And if you like the video, please do press a like and share with your friends if it helped you, and do comment what I should change in videos if you want any kind of changes, or what I do good in the videos. A bit of feedback would also be nice. Thank you.